Hi there. So I'm going to talk about 7.3 and just work through some examples and motivate some of the ideas for you. One quick comment that I want to make is technically in this section, we talk about double angles as well as half angles. Just so you know, we're only going to be working with the double angle formulas in this particular course. So I can give you our double angles formulas, and then I want to show you where they come from, precisely because they're things that we can easily derive from what we've done so far. So the two formulas that you need to be aware of, but again, you don't need to memorize because you'll always have access to these, is that the sine of 2 theta is 2 sine theta cosine theta, and that the cosine of 2 theta is cosine squared theta minus sine squared theta. Now, this the double angle formula for cosine actually has 3 different ways you can write them. I claim this is the same as 1 minus 2 times the sine squared of theta, which is also equivalent to 2 times the cosine squared of theta minus 1. Okay, now you might ask, where do these formulas come from? Well, I claim they come from what we covered in our previous section. So this is just kind of an aside just to show you that these don't come from midair. If I have the sine of theta plus theta, I think you'll grant me that's the same as sine 2 theta. Well, using our sine sum formula, that's sine of the first, cosine of the second, plus cosine of the first, sine of the second. First and second happen to be the same. And notice these are the same, so we have 2 of them. Okay, so that's where our sine double angle formula comes from. And then we can do a similar thing with our cosine double angle formula. Okay, cosine of 2 theta is cosine of theta plus theta. Well, our cosine sum formula said it's the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second. Okay, well, this is equal to cosine squared minus sine squared. Now, how do we get to these other versions? It's our Pythagorean identity. For example, we know that the sine squared of theta, okay, and I guess I'll just say sine squared plus cosine squared is 1. So another way I can write, for example, the sine squared of theta is I can say that's 1 minus the cosine squared of theta. And if I distribute throughout my throughout my parentheses, I get minus 1 plus cosine squared of theta. And that gives us the 2 cosine squared of theta minus 1. And in a similar way, we could rewrite this in terms, just in terms of the sine of theta by doing the same sort of thing. Cosine squared is 1 minus sine squared of theta, and then minus another sine squared of theta, which is where we get 1 minus 2 sine squared theta. This is extra. This is what you need to be familiar with in order to proceed through the section here. So what I'm going to do, as I've done in the previous sections that I've discussed, is I'm just going to take us through an array of examples that will hopefully help you clarify what you read in the section, as well as gain some practice and some skills to do your homework. So the first example that I'm going to do is I'm going to say if the cosine of theta is -4/5 and theta is in quadrant 2, let's find the sine of 2 theta, the cosine of 2 theta, as well as the tangent of 2 theta. Okay, notice this is the cosine of theta. You can't just multiply this by 2 because that's 2 times the cosine of theta, which is a very different thing than the cosine of 2 theta. So how do we proceed? Well, notice whenever we want to find any of these double angle formulas, what we really need to know in the end is what is the sine and what is the cosine. Okay, we have the cosine. We can certainly get the sine from there. Remember, we're in our second quadrant. We can just talk about our reference angle. We know that the cosine is adjacent over hypotenuse. This is negative since we're in the second quadrant, and you can use the Pythagorean theorem to get the length of this side to be 3. All right, well, we know our sine is positive in the second quadrant, so I think you'll grant me that. We now have the sine of theta is 3/5. Okay, so let's go through and find each of these 3. First off, the sine of 2 theta is 2 times the sine of theta times the cosine of theta. We found the sine of theta to be 3/5. We're given that the cosine of theta is negative 4/5. And so we get negative 24/25. All right, well, the cosine of 2 theta, we can use any one of these versions. It just doesn't matter. I'll use this one, the bottom one, just for no good reason whatsoever. So it's 2 times the cosine of theta squared minus 1. So that's 2 times 16/25 minus 1, which is 32/25 minus 1. In other words, 32/25 minus 25/25, which is 7/25. So we have found the sine of 2 theta. We have found the cosine of 2 theta. Now you might be asking, well, hold on a second. There was no formula here for the double angle for the tangent of 2 theta. But I think you would grant me that the tangent of 2 theta is the same as the sine of 2 theta over the cosine of 2 theta. And we just found that the sine of 2 theta was negative 24/25. And we just found that the cosine of 2 theta was 7/25. So notice once we found our sine and cosine, we were good. So we got negative 24/25. When you divide by a fraction, you multiply by the reciprocal, those cancel. So the tangent of 2 theta is negative 24/7. Isn't it kind of fun how like all of the techniques that we've been using are really like building on each other and we keep using the same sort of techniques? I think so. All right. Now let's just practice with this. What if I want us just to simplify the cosine squared of 28 degrees minus the sine squared of 28 degrees? So all I want us to do is simplify this. We're not going to actually do any computations. What I want to say is that when you see sine squared plus cosine squared, you got to think of your Pythagorean identity. But when you see cosine squared minus sine squared, you're going to start thinking about your double angle formula. Notice here, my theta is 28 degrees. So I claim this is the same as the cosine of 2 times 28 degrees. In other words, the cosine of 56 degrees. All right. What if I want us to simplify 8 sine 3x cosine 3x? Well, when you see a sine times a cosine, you want to start thinking about your double angle formula, okay? We know that 2 times the sine of theta times the cosine of theta is sine of 2 times whatever that angle is. So first, let's get this in the form of where it's 2 times something. think you would grant me that this is the same as 4 times 2 sine 3x cosine 3x. Okay, 4 times 2 is 8. Now, using this double angle formula, theta is equal to 3x. Okay, so notice theta is 3x. Therefore, we've got this 4 coming down, but now that's just going to be sine of 6x. Okay, right? Because if theta is equal to 3x, then 2 theta is 6x. Pretty cool. All right, so notice those were just simplify. Now, on the other hand, I could ask you to find the exact value of, say, the cosine squared of 75 degrees minus the sine squared of 75 degrees. And honestly, there are calculator approximations we can get, but notice if we say the exact value, we want our answer in terms of radicals, not a decimal approximation. So this should somehow signal to you that this is going to end up being one of our common angles. Okay, so you see cosine squared minus sine squared of theta. Our theta is 75 degrees. Using our cosine double angle formula, if theta is 75 degrees, this is equal to the cosine of 2 times that. In other words, we're wanting to find the cosine of 150 degrees. Well, I claim this is one of our common angles that we can find, okay? What quadrant is 150 degrees? I claim that's in my second quadrant. Here's 150 degrees. So to find the cosine, we ask ourselves, what's the reference angle? The reference angle is going to be 30 degrees. And we know that the cosine of 30 degrees is √3/2. And now we adjust for the quadrant that we're in. We know that the cosine is negative in the second quadrant. Therefore, this is equal to negative √3/2. All right, so let us now work through a couple more examples. These vary in level of involvement, I should say. I don't want to say that they vary in level of difficulty because it's just a matter of getting used to the techniques that you need to solve. So the first one I want us to do is solve sine 2x minus sine x equal to 0. All right, you cannot factor out a sine x here as it stands. Notice you're taking the signs of different things. These are inputs into a particular function. But you see a double angle here, you want to rewrite it using your double angle formula. Okay, so we know from our double angle formulas that the sine of 2x is the same as 2 sine x cosine x. And then we're subtracting off sine x. Notice now we have the same input. Now we can factor. Both of these terms have a sign in common. If I pull out a sine of x, my first term, I have 2 cosine x. My second term, I have -1. All right. Now I've got the product of two things equal to 0. And now we're back to solving our trig equations, essentially. So either my first one is equal to 0, or my second one is equal to 0. And we can continue on. Let's just solve this from 0 to 2 pi. Where is my sine equal to 0? It's equal to 0 at 0 and pi. And here, when we isolate our trig function, we're solving the cosine of x equal to 1/2. Well, we know our cosine is positive in our first and our fourth quadrant. This is a common angle here. I know that X is going to be pi over 3 or 60 degrees, but I'm using radians. And therefore pi over 3 will be my reference angle here. So you could say it's also negative pi over 3, or you can say that that's 5 pi over 3. Okay. So now let's solve. I have two more that I would like to do. The first one that I would like for us to solve is, how about solve 6 times the sine of 2t plus 9 times the sine of t equals 0. And again, we're going to solve that just going one time around our circle. All right, very much follows the same idea. Notice here it's the sine of 2t, here it's the sine of t. We have ourselves a double angle formula. So let's now rewrite this. So I claim that 6, the sine of 2t is 2 sine t cosine t, plus 9 sine t equals 0. So now I can get rid of my parentheses just by multiplying here. And again, we've got two terms here. I claim we can factor out a 3 sine t. If I do that, I'm left with 4 cosine t plus 3 equals 0. Well, I have the product of two things equal to 0. So either my first one is 0 or my second one is 0. Well, here to isolate our trig function, we divide both sides by 3. And again, we're going to get t is 0 and pi. Here, if I isolate my trig function, I'm going to get cosine t is negative 3/4. And notice this is certainly one we can do. This is not a common angle. So what we're actually going to need to do is use our calculators once again. Again, you want to be sure that since we're talking about radians here, we know we're talking about radians because it says solve it from 0 to 2 pi instead of from 0 to 360 degrees. So we know our cosine is negative in our second quadrant and in our third quadrant. So what we need to do is find the appropriate reference angle. And then in our second quadrant, we'll take pi minus that. And in our third quadrant, we'll take pi plus that. So what we want to do is find the cosine inverse of 3/4. So literally, I'm using my calculator. The inverse cosine of 3/4 is about 0.7227. So again, this is my first quadrant angle. I need to get my second and my third quadrant. So for my second quadrant, I'm going to take pi minus 0.7227. So the corresponding solution there will be 2.4189. And to find my third quadrant angle, I'm going to take pi plus 0.7227. And my other solution will be 3.8643. All right. Makes you appreciate when you're solving for common angles, doesn't it? All righty. So one more example here. This one's going to be a little more involved. It just has a ton of different solutions. All right, let's solve the cosine of 6x minus the cosine of 3x equals 0. Okay, notice you can't do anything right now. You're plugging 3x into your cosine function. You're plugging 6x into your cosine function. Okay, so what we want to note is that 6x is twice 3x. In other words, we can use our double angle formula here. Okay, now since this is cosine, we're going to want to use the double angle formula here that just involves cosines. There is no sense in introducing another trig function. So I'm going to say that the cosine of 6x using my double angle formula is 2 cosine squared of 3x minus 1. And then I have minus cosine of 3x. If it takes you a moment to look at this, remember, all I'm doing is I'm using my double angle formula here, okay? So now I'm just going to rewrite this as 2 cosine squared of 3x minus cosine of 3x minus 1 equals 0. So I just rewrote it so that I have it in a particular order. Now notice, now my inputs into my cosine function are the same, okay? This doesn't look very pretty at all. I claim essentially what I have is 2x squared minus x minus 1 if I let my x term be the cosine of 3x, right? Squared, not squared, and then our constant. Why do I rewrite it this way? Because I can factor this and know that I can factor this a lot quicker than looking at something like this, okay? I claim that this can be factored to be 2x plus 1, x minus 1. If you don't believe me, please multiply that out. Check it out. Okay. So what do I have then? Well, I've got the product of two things equal to 0. So either 2x plus 1 is 0 or x minus 1 is 0. This gives us x is negative 1/2. And this gives us x equals 1. Isn't it a sure statement of how far you've come when this is like a relief to do, right? Okay, well, essentially fine. I've gotten the x in this equation to be equal to two different numbers. What did x stand for? It stood for the cosine of 3x. So essentially what I'm solving is cosine of 3x is negative 1/2 or the cosine of 3x equals 1. I was just using x in place of that. All right. Hooray for back to trig, solving trig equations. What I'm going to do, again, going back to our previous ideas, is I'm going to simplify what's inside first, okay? In each of these cases, I'm going to let u be equal to 3x. So the first trig equation I want to solve is the cosine of u equals negative 1/2. And the second trig equation that I want to solve is the cosine of u equals 1. Okay. Now, let's solve this and get all solutions from 0 to 2 pi. All righty. So how do we do this? Well, where is the cosine equal to negative 1/2? Again, my cosine's negative in each of these quadrants. I know that the cosine of pi over 3 is 1/2. So pi over 3 becomes my reference angle in my second quadrant. And if pi over 3 is my reference angle here, that means I have 2 pi over 3 plus 2k pi. And in my third quadrant, I'll take pi plus my reference angle. So I get u is 4 pi over 3 plus 2k pi. Where is my cosine equal to 1? Thank goodness it's just at 0 plus 2k pi. We're not done though, okay? Notice we found what u is, but now what we need to do is solve this in terms of our x, okay? Whew. So what is u equal to? It's equal to 3x. So I claim from each of these three, I'm going to get 3x is 2 pi over 3 plus 2k pi. I'm going to get 3x is 4 pi over 3 plus 2k pi. And I'm going to get 3x is 0 plus 2k pi. All right, well, we don't want 3x. We want to know what x is. So for each of these, I'm going to multiply through by 1/3. Okay, so this top guy is going to then give me, if I multiply each of these terms by 1/3, I'm going to get 2 pi over 9 plus 2 pi over 3k. For the next one, notice I'm going to leave a space here. If I multiply through by 1/3, I'm going to get 4 pi over 9 plus 2 pi over 3k. And if I take my third one and multiply by 1/3, I'm just going to get 0 plus 2 pi over 3k. Almost there. The one thing we have left to do is now find each of our solutions in one revolution around. Now, one thing that might be easiest to do is just get denominators of 9, okay? At least for these guys, okay? So we can rewrite this as 2 pi over 9. We'll multiply and divide by 3. And this is going to be 8 pi over, 4 pi over 9. I'm thinking ahead, sorry, plus 6 pi over 9 times k. You'll see why I did that momentarily. Well, if k is equal to 0, from this guy, I get 2 pi over 9. If k is equal to 1, I'm going to have 8 pi over 9. If k is equal to 2, I'm going to get 14 pi over 9. Now, if I set k equal to 3, I'm going around my circle more than once. Okay, essentially, we want to go from 0 to 2 pi, aka 0 to 18 pi over 9. All right, so in this guy, if I let k be equal to 0, I get 4 pi over 9. If I let k equal 1, I get 10 pi over 9. And if I let k equal 2, I'm going to get 16 pi over 9. Woo, lots of solutions. Here, well, what do I get? I'm going to get 0 as a solution. If I let k be equal to 1, I'm going to have 2 pi over 3. If I let k be equal to 2, I'm going to have 4 pi over 3. And that's as large as I can get. Otherwise, I'm going around more than once. All right, this is as intense as it's going to get. Which, I mean, this is a lot. I mean, 9 different solutions. That's pretty crazy. Well, have a ball.